All right, guys, we're going to give these video lessons a go. I haven't done this before, and just to let you guys know, I'm going to be kind of going really quick because I'm trying to keep it to a 20-30 minute segment so I don't bore you to tears. We're probably about 5 days in, only about 175 more to go, but hopefully that didn't bum you out. So you guys, the course is going to be really tied to an excellent textbook, which you guys should be getting in a few, hopefully in a couple weeks. And so this lesson will be tied to chapter 1, and then you guys can use your textbook to supplement what it is we're covering here. And so you guys, I am going fast, and you guys know you can always stop the video. That's the nice thing about the video lesson, you can stop it. You guys aren't required to take notes on everything. I'm going to be going like super quick, so it's not as if you're going to be able to write everything down. In fact, I try to put the things that I want you guys to copy down in purple. I don't know if you guys can see with that, what's purple, because those are the things that I think are definitely things you want to write down, but you just want to write down things that you think are important. The things that you already know, don't bother writing it down, because remember, I'm not looking for a certain quantity of lecture notes, just some notes that indicate to me that you guys were watching these video lessons. So that's the Zen crossword puzzle, across nothing, down nothing. Okay, I don't know if you get that. Anyways, moving on. So chemistry, you guys know we were talking about that. Chemistry is the study of matter and the changes it undergoes. I figure you guys know, a lot of you guys know if you've already had me, I like to do demonstrations. Here's a demonstration because you guys, the thing about chemistry, it's about matter, not just matter, but its changes. So we want to look at one of those. Man, this is hard. I'm used to interacting with other people. Obviously, I can't really interact with my phone right now. Oh, and so you guys, I'm hoping the angle's right. You guys are going to see it's kind of difficult. I'm kind of just doing this myself. So I'm not really changing things up. I'm hoping you guys can see a clear screen. We're just trying to do the best we can. I guess it's better than nothing, right? Okay, so anyways, so what I have is I have a penny. I don't even know if you guys can see that. It's a penny. It's kind of like an ugly penny, but it's a penny. You're familiar with a penny. And then here, in this beaker here, I have nitric acid. And you guys kind of just, right, you can describe matter, and you could describe a penny as like shiny, brown solid, and then nitric acid is a clear liquid. I don't know if you guys can see the fumes coming off here. It's very concentrated. You gotta be very careful. That's why I got my goggles on. So I'm gonna put the penny in the flask, and then I'm gonna add some nitric acid. Okay, so we got matter here, and we want to see the changes it undergoes. Okay, so I bring the nitric acid in contact with the penny, and we're gonna use something here. Okay, so hopefully you guys can start seeing some changes going on. I don't know if I'm too close, too far. It's not going to be ideal. You guys, I just kind of want you guys to make some of the observations there. I don't want to say too much about it. I might even ask this as a question. And you know what? I will tell you this. What's coming out there is pretty noxious, so I have to, so I don't kill myself, I'm going to have to put it in a fume hood. And you guys, I would show you the fume hood for those who haven't been to my class yet, but once I move that camera, I don't know if it's going to be in the right position, so I got to leave it. So anyways, I put it in a fume hood. So we kind of made some observations. You know what? And what I need to remember to do is come back to that. If I forget, you guys remind me. Oh yeah, you can't remind me because you're not speaking back to me. But nonetheless, I do want to look back after some of that. I don't even want to really explain it because I want you guys to ultimately be able to explain it. But you saw, I mean, it does look pretty cool. I wish you guys could see more of it. But once again, so I don't kill myself, it's in the fume hood. Then we're gonna, but you did get a kind of an idea of what was happening there. Okay, so chemistry, you guys, it's all about matter and matter changing. The scientific method, you guys, that's back what you guys learned back in middle school. It starts with making observations, right? We observe something, then you begin to ask questions like, how did that happen? Or maybe you identify a problem, and then you pose a hypothesis, which is a possible explanation of the phenomena or a possible solution to the problem, and then you test it, right? That's what science is all about. And unfortunately, we can't, we're not doing labs right now, but hopefully we get back in the classroom, you guys will be able to do it. And then you reach conclusions, and if it always reaches the same conclusion, test after test, then you can form what's called a theory. But even then, once a theory is established, which helps us to understand natural phenomena, we continue to carry out experiments and then modify the theory. Like I said, I'm going quick here, guys. You're not going to be able to copy everything down. Don't worry about that. So matter, you guys, there's different things that matter. I don't know if you guys can see this. You got matter is essentially made up of individual atoms of elements, And then atoms of elements can come together and form what are called molecules. And you can see here 2 blues indicating 2 of the same type of atom. But if you get 2 or more different types of atoms come together, that's what we call a compound. Okay? And then you can have mixtures, which is 2 or more actual different substances would make up a mixture. So these are just different ways to classify or categorize matter. We have pure elements, we have compounds, and we have mixtures. So atoms are the building blocks of matter. Here's oxygen, consists of 2 oxygen atoms. It says each element is made up of the same kind of atom. An example, yeah. So, and then compound, an example would be water, ethanol. You can see the white or the hydrogens and the red is the oxygen. You guys should know water is H2O. Carbon dioxide is CO2. That's a carbon, 2 oxygen. You guys can see these are all examples of compounds because they contain 2 or more different elements. States of matter. You guys should be familiar with this back in middle school. You have gases, liquids, and solids. And I don't know if you guys look at that. The main difference you guys should see there is in the gas phase, the molecules or the particles that make up the gas have a great distance between them, and that's why gases are compressible. But if you think about liquids and solids, the atoms or the particles are really close together, and that's why you can find it very difficult to compress solids and liquids. Properties and changes of matter. There are what we call physical properties. For example, a physical property, when you're describing the penny, a physical property of the penny is that it's a brown solid, for example. Physical property of the nitric acid is that it's a clear liquid. And some other physical properties are like boiling point density. Each substance has its own unique density, has a unique boiling point, the temperature at which it goes from a liquid to a gas. And those are properties that just depend on the substance itself. But contrasting physical properties, they're what are called chemical properties. And these are properties that are based upon when the matter changes, when it changes from one form to another. Some examples of chemical properties would be flammability. Like if I had a piece of paper, right? I have a piece of paper, good old burning of paper, right? It's got certain physical properties. It's a white solid. But one of the chemical properties is you would say paper is flammable. You can see it's undergoing a chemical change. It's forming. You can see, and you know it's a chemical change. You look at it, you can clearly see that the properties of the ash and what you don't see is the carbon dioxide. You clearly have different substances now than you had originally, indicating a chemical change. So corrosiveness, that would be like, for example, rusting, right? Things like that. Physical changes, these are changes in matter that do not change the composition of a substance. Like, for example, a physical change. The paper's flat. Now I did this. Did it change? It did change. Did its composition change? No, it's still paper. It still consists of the same carbon, hydrogen, oxygen atoms in the same ratio, but it did change. We would call that, for example, a physical change. Another good example of a physical change would be a change in state. You take water, you heat it up, what's it going to do? It's going to boil or evaporate. But you think about it, you started with what? Liquid water, and when it evaporates, what do you have? You have water vapor. It starts as H2O. What does it end as? Oh, it's still H2O, it's just the molecules are more separated. The chemical composition has not changed. That would be an example of a physical change. Chemical changes, which we just kind of observed one. In fact, yeah, let's go. Okay, guys, you can see what we have here, and I don't know if you guys can see that better. I can't even check. I don't have a videographer, sorry, I'm not a professional. But you guys can see now, and now you could pretty much describe, you're like, oh dang, that's like a green, bluish liquid. That wasn't there before. Obviously, what we have here is different than what we had before, indicating a chemical change occurred. And all a chemical change is, all a chemical reaction is a rearrangement of atoms. So I would imagine a question you guys would have, what would be a question you'd probably have, right? If you're using your observational skills, everyone can observe that. But I'm hoping when you guys make observations in life, you guys are you're moving on beyond just the what, when, and where's. Like everyone's asking those questions. They're asking like, well, what time is it? What's for dinner? They're asking the when question. When is this class over? When am I going to go on vacation? They're asking the where questions. Where are you going to go? Things like that. Those are all base level questions that everybody asks. I'm hoping you guys have a more elevated intellectual approach to life, and you're going beyond just the base level what, when, and where, and you're going to ask the questions like the hows and the whys. So the question here, well, you know what? I might even have a what question. I would imagine a question you guys have, what? Or no, I would imagine it was a where question. Where is the what? Where's the penny? Where's the penny? That would be a question. question I would have. Where the heck did the penny go? I don't know. That's where, but that, and then you would begin to, ask the how and the why as a result. But anyways, so I want you guys to think about it. Just think about that. And maybe we'll ask that question maybe on one of our synchronous meetings. What happened to the penny? I want you guys to just kind of think about it. Just think about, you already know some about a penny. You're thinking penny is primarily what? You're thinking, oh, it's copper. Think about, where did it go? Okay, so just something to think about. Now check out this. This will be an example of a chemical reaction. Here we have hydrogen, which is H2. You see two, I don't know if you guys can see that, two hydrogen atoms together makes up a hydrogen molecule. And you have O2, two oxygen atoms. Well, when those combine together, and if you just ignite it, what's going to happen? They're going to combine together. What do you think it's going to form? Water! It's going to form water. You've got H2O, two hydrogens, one oxygen, and it will have, it'd be highly exothermic. We'll talk more about that another day. But that would be an example of chemical reaction. Here's the actual reverse. You can go both ways. In that case, we took hydrogen and oxygen and combined it together to form water. In this case, you guys just look at it. I don't know if you guys can see it. What does it look like? We've got a battery hooked up with these electrodes, and it's in water. So we're passing electricity through water, and what do you think's happening? We're taking the water molecules, and we're actually decomposing it. It's kind of the reverse, and decomposing it into its constituent elements, which are oxygen and hydrogen. So we're kind of going in reverse. So that's how you can get, and here you're going to form a greater volume of hydrogen. You guys should know that, because remember, it was H2O. There's twice as much hydrogen as oxygen. So the one that has more air here that displaced the water is the hydrogen, and then that would be the oxygen. Separation mixtures. You guys, most things in the most common form of matter is not pure elements, it's not pure compounds, it's mixtures. If you guys think everything around you, what are you? You're a mixture. You guys look at your table. What's your table? What's your, anything in your room? I don't know where you guys are watching this. Pretty much everything you point out is going to be a mixture. You might point to a piece of metal and say, oh no, but even that would be a mixture, because you guys know most metal is not like pure iron. Most of the metal you guys encounter is going to, but it's going to be a mixture of various metals to get in order to get certain properties, and we call those mixtures alloys. But anyways, most things are mixtures. So oftentimes as a chemist, when we want to analyze and work with different things, we need to separate mixtures. One way we can do that is distillation. You guys check it out. Those of you guys, when you guys are in my classroom, you guys are going to find there's distilled water. Distilled water is just pure water. The water you guys get out of the tap is not pure water. It's got minerals and other things that it accumulates when it's traveling through the pipes, right? And for the most part, you guys, you can drink your water. It's perfectly safe to drink. But if we wanted to distill it, that basically means get pure water. So we've got our regular water here with its minerals. In this case, it says salt water. And look at it. What can we do to it? We can boil it. What's going to happen is we apply heat to it. What's going to evaporate first? The water, because the water has a much lower boiling point than the substances that are in it. So the water evaporates, and then as it evaporates, it forms a gas. And then you can see in this apparatus here, then it declines here. So just due to gravity, that vapor will go through the tube. But then what we can do is we can pass cold water through. You can't really see it, but there's a tube within a tube. So we pass cold water in an outer tube. What's that going to do to that water vapor? Well, you get it cold, the molecules were moving really fast initially, then they begin to slow down, come back together, and form regular water. So then what do we have here? We just have pure water. That's what we call distilled water. Where were all those minerals and salts and other things that we want to get rid of? They're just back here because they hadn't vaporized yet. There's also the process of filtration. You guys should know this. In filtration, what are you separating? A what from a what? Think about when you're making coffee. You're separating a solid from a liquid. That's how. So you have a filter paper. The solid, which tends to be larger particles, is not going to pass through the filter paper, and the liquid pass through the filter paper, and therefore you can separate a mixture of a solid and a liquid. Chromatography, you know what? That's another, like if you guys take a marker, you guys know a black marker, how you get black? It's really just a mixture of different pigments. And you guys know if you take a piece of paper, you guys know if you get it wet, you have the capillary action where the water moves through the paper. And in this case, the different particles that make up the different colors, the different pigments, have different sizes. And therefore, they're going to move with that moving water at different rate. And you guys can see the blue moves faster with the water than the purple, and so therefore it kind of separates out the colors that made up that original black marker. So just chilling. Hopefully you guys, I know a lot of you guys were chilling over the summer, but we should be just chilling right now. We don't want to be like these fools right here. He says, what's on your arm? He said, oh, it's my new Fitband. So you got, one of those fit trackers. My wife got one of those. He said it tracks how many times I press the TV remote buttons. Hopefully you guys are doing a little more exercise than just hitting that remote. Okay, units of measure, you guys, that's the big thing today. In fact, that's what your assignment's going to be on. We have matter, we're studying matter, and we have to be able to measure it, so we have to use units in which to measure matter. Here's some popular ones: kilogram, which we use to measure mass. The standard measurement we use for length is a meter. Time we use second, you're familiar with that, and then temperature is actually Kelvin. So these are the international system units that we use. It's a different base unit is used, okay? The metric system, you guys, when you have 10 to the negative 3, does anyone know what the prefix would on that would be? That would be like a 0.001. 10 to the negative 3, that would be milli, M-I-L-L-I. 10 to the negative 6, anyone know what that is? That's 0.00001. So that's something really small, which you're dealing with very smaller. That would be micro. 10 to the negative 9, I don't expect you guys to know that. That's nano. You're like, nano. 10 to the negative 12 is pico. You're like, pico. We got a pico. 10 to the third, you guys should maybe know that. That's 1,000. So if you have 1,000, like if you had 1,000 meters, what's the prefix? Kilo. And then 10 to the 6, that's actually mega. We would know that as like a million, right? 1 followed by 6 zeros. So this is all them. I don't know how, and obviously at this point you could, just stop the video. I don't know if you can see it. Hopefully you can, but it's just kind of showing some of those. You guys know we got different temperature units we can use, and that's where it gets kind of confusing. You're like, dang, why can't we just have one and get used to it? Well, in the most of the world uses the Celsius scale. Therefore, those of you guys who were born in Mexico, spending time in Mexico, you guys are better off because the Celsius scale is far better than the Fahrenheit scale, which we typically use in the U.S., which is kind of a horrible scale. And actually, despite that, the one that the international science community uses is actually the Kelvin scale, and there's a reason for that. So this is how we measure temperature. By the way, some of you guys might remember from last year what temperature is. Temperature is the average kinetic, and you remember when you hear kinetic, you're thinking movement, average kinetic energy of the molecules. So obviously, the faster the molecules are moving, the higher the temperature. The slower they're moving, the lower the temperature. So the Kelvin scale is actually the international system used for temperature. It's based on properties of gases. There's no negative Kelvin temperatures, and you guys, this is why. And so you guys, a lot of times we have to be able to convert, and it's really easy to convert because you usually want things in Kelvin when we're working with different gases. So you take your Celsius temperature, right? You have your normal thermometer we measure in Celsius, and all you do is add 273 to it to get the corresponding Kelvin temperature. And so it says, what's the significance of the Kelvin scale? The significance is it ties to this. Notice there's no such things as, you guys know you can have negative Celsius, right? You guys, right? Because you guys know water freezes at 0 degrees Celsius, but water can get much colder than 0 degrees Celsius. It could be negative 10. In fact, in your freezer at home, it's probably like negative 10 degrees Celsius in your freezer. But with Kelvin, there's no negative temperatures. So what does 0 Kelvin mean? And this is why it is considered an absolute measure of temperature, because 0 Kelvin means there's no molecular motion. So 0 actually means no motion, and that's why it's the preferable one, because you guys would understand. Can 0 degrees Celsius, does that mean no molecular motion? No. And what's the evidence for that? Because there's what kind of Celsius values? Negative values, indicating molecules can move slower than 0 degrees Celsius. Okay. Density, you guys should remember this. This is actually middle school too. Each substance has its own unique density, and density is the ratio or the measure of the mass of a substance, M, compared to its volume. So obviously if something had a very heavy mass and a low volume, it's going to have a high density because this number would be big and this number would be small. You take a large number divided by a small number, you get a large number. What if something had a very little mass, it was very light, and it was like a large volume, like a beach ball? Well, if this number is small and this number is large, what kind of value do you get if you take a small number divided by a large number? A very small number. And so it would have a low density like you would expect for gases because the molecules are spread out. So you guys can see I went really quick. We're just going to end right there. All right, hope you guys made it through the whole thing. We will see you guys next time. Bye.